Okay, so let's continue with chapter 2. I believe we covered resistors in series and parallel. And now we will insert a source into the circuit. And let's see, let's bring up the class notebook here. Okay. All right. So resistors in series, resistors in parallel. Then we combine both techniques to determine the total equivalent resistance of a resistive network. By the way, when we say network in this case is a synonym of circuit. Okay, so if we say network, whether we say circuit, they mean exactly the same thing in this context. So now we introduce a source into the circuit, into this network. So we have this combination of resistors, which is now receiving energy from a voltage source. So we will use the technique of finding Req and applying Ohm's law, KCL and KVL to determine the voltages and currents that will appear in this circuit. Okay, so the first step in this is to reduce the network of resistors to a single resistor, meaning we have to determine Req. Okay, Req. The way we do that is by removing the source and analyzing between the open terminals. So we remove the source and we redraw the circuit with simply the resistors in place. So no matter which circuit it is, this would be the standard operating procedure. All right. Okay, so this is R1, R2, and R3. So again, the first step to determine Req is to remove the source from the circuit and analyze or measure Req, total equivalent resistance, between those terminals. It is also stated as finding the total equivalent resistance, Req, as seen by the source. Okay, as seen by the source. And this phrase, as seen by the source, or the perspective of the source, is something we will look at again and again throughout the entire throughout the entire course. So as an example, right now we have, let's say, 10 students in the classroom or 10 people in the classroom, right? We got 1, 2, 3, 4, 5, 6, 7, 8. From my perspective, I see 8. But there are a total of, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So from my perspective, I see 8 people. But if somebody's outside the room and asks how many people are in the room, it's 9. So if I am counting the number of people, from my perspective, it's only 8. So it's kind of like that. You remove the source from consideration and find Req between those terminals. And then you apply our technique, reduce it down to one single resistor. In this case, we have R1 and then the parallel combination of R2 and R3. Okay, and then of course Req would be the series combination of R1 plus R4. Okay, so if we solve this, we obtain, what do we obtain? 10 plus 30 in parallel with 60. 30 in parallel with 60 is 1800 divided by 90. So 20 ohms, right? Product of the two divided by the sum of the two. And 10 plus 20 gives me an Req of 30 ohms. So now after I find Req, I'm going to connect it back to the voltage source. Let's take a 10-second pause while you write it down, think over it. Let me know if you have any questions. Any questions from anyone? Step number 1 makes sense. I believe this is also covered in your physics classes, right? Okay, so now we have a voltage source, we have a resistance. What is the third quantity that we can determine using Ohm's law? Current, I. Which direction is the current going? Up or down for the source? Up. Yep, that is correct. For a source, it supplies energy, losing power, it's supplying power. Current always goes from minus to plus. So remember chapter 1 where I said when we begin circuit analysis, we have no idea what direction the voltage or current is moving. We have no idea about the direction of the current. We have no idea about the voltage polarity for certain components. So we assign the polarity and direction arbitrarily. This is based on assumptions, and the assumptions are based on logic, on certain rules. In this case, we know current for the source has to go up from minus to plus. It has nowhere else to go except around the circuit. There's only one resistor and one source in there. So the current is going from minus to plus and makes its way around. It's entering the resistor from the top. Resistor is a passive component. So what voltage polarity do we have at the top? Plus or minus? Plus. Passive components are receiving energy, they're receiving power. And so the current always goes from high to low, from plus to minus. And so from this, we can write, or we can display the voltage polarity as plus minus. Obviously, this is just a simple circuit because it only has one source and one resistor, but the fundamental principle applies to any circuit. Even if you make the assumption opposite of what the rules or the logic dictates, you would still obtain the right answer, except you would get a minus sign at the end. That's all. So apply Ohm's law. And I can write I is V over Req, 90 divided by 30 to 3 amps. So total current I flowing through the circuit is 3 amps. Any questions? Straightforward so far? Okay. All right, now, now I'm gonna go here. We expand the circuit back up step by step, okay? So here, we reduce the circuit in 2 or 3 steps. Now we will expand the circuit back up in the reverse order, 1 step at a time. So if I was going to do that, what would I get? Voltage source, my resistor R1 and resistor R4. This is still Vs. Current I is still flowing in this direction. I can state R1 has plus on the left, minus on the right, and R4 also has plus up top and minus at the bottom. Okay. Think on that. Let me know if you have any questions. I'm going to change out the color. Any questions? Yes. Oh, so the reverse order, as in this was step 1, removing the source. This was step 2. This was step, actually, you know what? Let's not do 1, 2, 3. A, B, C. And now reverse order would be going from C to B to A. So let me note that down. Expand in reverse order. So the question being asked was, what does reverse order mean in this context? And reverse order means we are now determining the voltage and current for every step that we took to find Req. So every step along the way allows us to find the voltage and the current. See, we found the total current I in the circuit, but we cannot directly go back to the beginning. We cannot directly go back to step A to find the voltage or current. We have to find the voltage or current for the preceding step. Then we use those quantities to go back up again, one step at a time, without which we cannot find the voltage at the top. So it will be C to B to A. So now we already have I. We can find VR1 and VR4, right? So we apply Ohm's law again, determine VR1. VR1 from Ohm's law is it's just 10 times 3, 30 volts. And VR4 is 20 times 3, 60 volts. And of course, if you apply KVL, 30 plus 60 should sum up to 90 volts, which is the supply voltage. Important thing to keep in mind, and again, our brains do not think about it in a conscious manner, is that voltage or current would be directly proportional. Sorry, voltage is directly proportional to the resistance. Current is inversely proportional to the resistance. Meaning if the resistance is smaller, then the voltage drop across the resistor is smaller. The higher the resistance, the higher the voltage. Current is the opposite, right? I is V divided by R. So the higher the resistance, the lower the current, and the lower the resistance, higher the current. Okay, so you have to keep that in mind. 10 ohm resistor, 30 volts, 20 ohm resistor, 60 volts. And current would be the exact opposite. Okay, so now this was step B. If we go to step A, which is where we want to find the currents for R2 and R3. Remember, R2 and R3 are in parallel, so the voltage across both of them would be 60 volts. In circuits, electrical engineering, this is a standard accepted convention. When you see something like this, plus and a minus sign with some numbers in between, it indicates that the voltage between those two nodes is 60 volts. And this node is exactly the same for both resistors. So the 60 volts applies to both of them. It applies to R2 and it applies to R3. This is R1, this is Vs. Now, a total current I is only going up to here. When it hits this junction, it splits in two. Okay. This is IR3, and the current coming down here would be, just label it IR2. Okay, IR2. Naming convention is up to you. You can label it whatever you wish. Okay, IR2 and IR3. We have the voltage across R2 and R3. Apply Ohm's law again and find the current. Let's take a 10-second pause before I do that. Let me know if you have any questions. Yes. Yes. Both would be 60 because they're in parallel. Yeah. Question being asked was about VR2 and VR3. So VR2 and VR3 is basically VR4. So let me write that down. Therefore, VR2 is equal to VR3, and both of those are equal to VR4, which is 60 volts. Any questions about anything so far? Does it make sense? The steps and the procedure? Okay. All right, then one final step is to apply Ohm's law and find IR2. So it would be VR2 divided by R2. 60 divided by, what is R2? R2 is 30 and then 60. And IR3 would be VR3 over R3, 60 divided by 60, 1 amp. 30 ohms, smaller than 60, you get a larger current, which is 2 amps. 60 ohm resistor, same voltage, smaller current, 1 amp. Now we have the voltage and the current for every single resistor. We can find the power, we can find the energy if needed. Okay, let's take a pause. Write it down, think over it. Let me know if you have any questions. Any questions? You ready to move on to examples? Okay. All right. Question being asked here is just calculate the currents, but we can use this technique to find voltages, currents, power, whatever we need. Okay. So let's take a look at the first circuit. What do we see? Simply the same circuit as the previous one, except we have one more resistor in parallel. And so for circuit A, what you would need to do is reduce the three resistors on the right to one single resistor. And you would proceed in exactly the same manner as the solved example in the previous slide. This is R1. I'm going to label this as R5. And R5 is the parallel combination of R2, R3, and R4. Exactly the same procedure as the previous slide. Okay. Design is for student practice. How about C? Let's take C first. We'll talk about B later. C is also similar. You have R1. You have a 40 ohm resistor, R2. And we would combine R3 and R4 in series and state it as R5. And then we realize it is the exact same circuit as the previous one. Okay, let's take a pause while you write it down. Let me know if you have any questions. Yes. Meeting passcode is on the front page of the Canvas website. Do the two circuits make sense? One other thing I would like to note is that R3 and R4 are in series because they're connected at one junction. Okay. Whether there is a bend in the circuit diagram or whether it's a straight line, that doesn't change the fact that electrically speaking, that is a junction point. It is a node where two components are connected, and so they are in series. No more than two connections at that node. So R3 and R4 are in series. And when we combine them, we see that they are 40 ohms. So it's 40 and 40 in parallel. So this is 40. This is also 40. If you have two resistors with the same value in parallel, it's basically half. Req for R2 and R5 is 20 ohms. Okay, it's 20 ohms. Let's take a 10-second pause. Any questions? Yes. I'm going to do it now. It's a current source, so I wanted to keep it for the last. So A and C are very similar circuits. Okay. Let's talk about B. First thing about B is that it's a current source, but the procedure remains exactly the same. Okay. Procedure doesn't change. We find Req. And in this case, instead of finding the current, we now find the voltage across those resistors. So you apply Ohm's law and you determine what the voltage is going to be. In this case, I'm going to have current, actually, you know what? Let's remove that. And we can see that R1 and R2 are in series and R3 and R4 are in series. So I'm going to go ahead and combine them together. We'll call this R5. R5 is R1 plus R2. And here it will be R6. R6 is R3 plus R4. This gives me 20 ohms. So does this. Okay, both of them are 20 ohms. 20 in parallel with 20. My REQ is simply 10 ohms. Right? If you have multiple resistors, all with the same value R, equivalent resistance is R divided by N. So now I will plug the current source back in. And I would find the voltage Vs. When you have two components connected like this, it's a very unique circuit in the sense that the two components are in series and they are also in parallel. Okay, so the current is the same for both components and the voltage across those two nodes is also the same. So here in this case, Vs is 2 times 10, gives me 20 volts. 20 volts. And then, of course, 20 volts is also the same voltage across both branches, across R5 and across R6. So if I expand the circuit back up, R1, R2, R3, R4. And the voltage across all these nodes is 20 volts. Current IS flows here. Some of it goes down here, some of it goes down here. We can apply Ohm's law and find the total current. Let's call this I5 and I6. And I5 would be 20 divided by 20, 1 amp. And I6 is also 20 divided by 20, 1 amp. And now you have the current through all 4 resistors. You can apply Ohm's law again to find the voltage. And that's it. Think over it. Let me know if you have any questions. There are no questions. Let's take a break. 11:02. Let's pick it up again at 11:06. Sure. Yeah.